right, so we're gonna go ahead and do this quiz, and I want to talk to you a little bit about what's going on here. So it says we got this titration, and you know I love pictures, so let's go ahead and draw this titration out. It says, oops, a little bit of water on something. And you can probably hear my kids jumping around upstairs in the background, so I'm sorry for that. This is the quietest I've had it all week. So I had some kind of titration. It says that in this solution, we have 100 milliliters or 0.100 liters of a 0.0200 mole per liter solution of iron 3+. To which we're going to be adding 0.100 mole per liter solution of copper plus. And it gives us some other information. It says you got a mole of a strong acid in there, 1 mole per liter of this perchloric acid. And it also talks about the type of electrode you're using to measure this, which we will have to eventually account for. We have to take out the voltage that is contributing to the overall cell. We have a platinum wire in here, and we're measuring it, the voltage right there. It gives us a little bit of other information, but essentially, let's just go ahead and go through each one of these, and then we'll talk about each point as we get there. So the first question says, write a balanced titration reaction. So we're looking for what's actually occurring here. Well, we know that it already kind of gave us some information. It says you're taking this iron 3+, and you're taking copper 1+, and you're going to get iron 2+ and copper 2+. So we've got iron 3+ plus some copper 1+. It's going to be a reaction occurring to give you iron 2+ and copper 2+. It looks to me like it's 1-to-1 reaction. A really quick way to do that is just add up all the charges on one side, see if that equals the charges over here. Over here I get a +4, over here I get a +4. It tells me automatically that it's balanced, so I'm good to move on. So write the balanced reaction, check. Now, one of my natural instincts is as soon as I've got a redox reaction written, I like to break it down to the half reaction just because it gives me an idea of what's actually occurring. So I would look at the iron and I say, okay, well, Fe3 plus some electrons are going to be forming Fe2 plus some electrons. I should say 1 mole of electrons. And the same thing with copper. Here we've got copper 1+, but the electrons are going to be over here, forming copper 2+ and some electron. And again, that's the exact same reason you want all the charges on each side to add up to equal the same. Over here I got 3+ and a negative, that gives me a 2+. Over here I got a 2+, that's good. Over here I got a 1+ from the copper, and a 2+ and negative gives me a 1+ from here. So everything works out. Now, it's important to note that even though these are the reactions, the next question wants the redox, or the reduction reactions. So it wants the one where we're gaining these electrons over here. And so in looking at it, it says copper plus electron goes to what? So here, our electron is on this side. So if we took this reaction and we flipped it over, that's when we would get what it's asking for right here. So it's copper 2+ plus an electron is yielding copper plus. And this is important because this is what we're going to be using in our Nernst equation is this information from over here. And then the iron is pretty straightforward. It's pretty much what we have written. Iron 3+ plus an electron is forming iron 2+. All right, so check on that. In case you missed this part, let me rewrite it again. It's Fe3+ plus Cu plus, yielding iron 2 and copper 2. Now it says write 2 different Nernst equations for the cell voltage. One before the equivalence point and one after the equivalence point. And it gives you a little bit of information. And right now we should be like, what is going on? And hopefully it's not is not too terribly rough because we understand that as we're adding, let's look at this, as we're adding this copper, essentially it's being used up very quickly, and the main contributing thing to the voltage is still going to be the iron until we run out and we use up the iron at the equivalence point. Then we're going to be looking more at the copper being the reactant because we have excess copper. So right now, before the equivalence point, we're only focused on the iron, and that's why the Nernst equation that we're going to write has to focus only on the iron. And again, we have to pay attention to the fact that we've got this silver electrode contributing 0.197 volts, and that again, that's from the Ag plus electrode. So before what we're looking at our E cell, and maybe even before I get here, I should note that when we talk about E naught right here, it's talking about standard conditions. 298K, it's talking about this reaction occurring with 1 mole per liter of each of these things. We don't have 1 mole per liter of each of these things, and that's why we no longer have E naught, we just have E cell. And this is dependent on the conditions. There are 2 different equations. There's another equation in which we use the natural log, and it's got RT in it. That's for when we have a temperature dependent reaction. Right now, there's no mention of temperature, so we should assume that we're talking about the Nernst equation, which is as follows. So E cell is equal to, so before, again, I told you we're looking at the iron part before the equivalence point, and that would be iron's voltage, 0.767 minus 0.05916 volts, divided by the moles of electrons that are being moved. This is only 1 electron. If this had been 2, we would put a 2 there, or 3, it would have been 3. It's just 1, so we put 1. Times the log, and we're looking at the products over the reactants. Well, the products over the reactants here are from these reduction half cell reactions. So we're looking at this iron 2 over iron 3. Now these can be in moles or in moles per liter. The reason is because they're all in one single container. So no matter what, you have the same volume, and the volume divided by the same volume is going to cancel out and equal 1. So you can use these in moles or moles per liter. So before, it'd be this, and we have to factor in the fact that that silver is contributing 0.197 volts. So we subtract that out. Can you see this? Please tell me you can see it. Doesn't look like you could. Okay. Sorry, I know how annoying this is, but it's also annoying to edit a video and start all over again. So hopefully you can understand that too. Okay, and then we have to have an after. So afterwards, we're gonna have an excess supply of the copper. So our after equivalence point, our E cell will equal that of copper, 0.161 volts. So it's E naught minus 0.05916 volts over 1 electron times the log of copper's reduction, which is Cu plus over Cu2 plus. And in the same situation, we want to subtract out the 0.197 volts. Now it says calculate the equivalence volume of the reaction. This should be fun. This is just standard stuff. So let's see if I can zoom out for you here. This should be fun. It's just normal calculations for a titration. So we have I don't know where I put it. Anyways, we have that reaction where we have 100 milliliters of a 0.02 mole per liter solution, and we're figuring out the equivalence volume with 0.100 mole per liter. So we use this reaction and this stoichiometry within this reaction to determine that. So we start with 0.100 liters of our iron, and we know that in a liter there's 0.0200 mole of this iron 3 plus. We know based on the stoichiometry of the reaction that for every mole of iron 3 plus, we have a mole of copper. We require a mole of copper, 1. And we know that there are 0.100 mole in a liter of this copper solution. So 0.100, 0.100 happen to cancel out, and we're left with 0.0200 liters of the copper solution. In other words, when we titrate that solution, here we go, found it. When we've added about 20.0 milliliters, we'll be at the equivalence point here. Okay, and last but not least, it actually has us doing some math. This is great. Now calculate the E cell after 5 milliliters of copper has been added. Well, after 5 milliliters has been added, this gives us a big hint as to which equation we're looking at. So if we'd added just, if we'd added 20 milliliters, we had been looking at this after equivalence. Actually, we would have been looking at a whole different thing. It's at the equivalence point. At the equivalence point, this is going to be the log of 1, which is 0. All this is 0, so you just have the standard cell potential minus the 0.197. That would be your answer. However, this looks like it's before our equivalence point because we've only added 5 milliliters. We haven't added 20 yet. So before our equivalence point, let's look at what happens in terms of the reaction itself. Again, our reaction is iron 3 plus copper plus, yielding iron 2 plus and copper 2 plus. An ice diagram tends to, or an ice table, tends to do us some service here. We know that when we first started, we had 100 milliliters or 0.100 liters of a 0.0200 mole per liter solution of iron. In other words, we had 0.002 moles of iron, and I'm going to kind of reduce some sig figs to save some space. Copper, it says we added 5 milliliters. If you remember, we're adding 0.005 liters, it's a 5 milliliters, of a 0.100 mole per liter solution of copper. So here we get 0.0005. Everything that can react will react, so we'll go ahead and lose that 0.0005 of this. We'll also lose 0.0005 of the iron to gain over here plus 0.0005 and plus 0.000. So here we get 0.0015. Here we have nothing. And here we have positive 0.0005. I'm not worried about this copper. We've used up all of this copper, so copper is not contributing to the voltage at all. Again, before the equivalence point, we're only looking at iron. And therefore, when I go through to do this, I'm using the before equation, which, if you remember, is E cell equals 0.767 minus 0.05916 volts divided by 1 mole of electron times the log. Now you could take each of these and divide them by the 105 milliliters that's in there, the 0.105, but you'll get the same quotient. So we're taking products over reactants here. So we're looking at that of iron 2, 0.0005, divided by iron 3, 0.0015. Don't forget to subtract out the 0.197 volts. And this gives us an overall answer of a voltage of 0.598 volts. And hopefully that's what you got. If it is not, throw it on the discussion board, because I'd love to answer some questions. All right, thanks y'all. Have a good day.